Hey everyone, welcome to another project video and first of all we'll solve the error that we actually left our code at. Okay, so we're going to solve the error that we actually left. So yeah, the error what we were seeing yesterday was expected 2D array but got 1D array instead. So this. Okay, so what we actually did wrong here is that I actually passed the wrong parameter. Okay, I had to pass here the x, okay, the features, and I had to pass here the y variable, or you could say the label. Okay, as you could see in the documentation, it is in this code what we have the x, the feature, and the label. Okay, that we had to pass, and I did it wrong. Now you could see that we'll get a score of 1. Okay, and if I replace to y val, we'll get a score which actually makes sense, which is around 0.65. That is great. Okay, so that is the thing that we did wrong here, and that was we were getting error. Okay, and right now I am just removing it because we don't need the score, for checking our matrices. Now the first thing that we have to do is that making a to-do list, that what we have to do. Okay, so today what we have to do is that that I have built the model. Okay, linear regression. Okay, I have actually fitted the value. Okay, so the first thing that we'll do is that building models. First one is linear regression, and the second one is SVM, linear SVM. Okay, linear SVM building model, and last one, the second one is building pipelines. Okay, so within the models we'll be building pipelines, and third thing that we have to do is what we could do building pipelines. We will actually do the hyperparameter tuning. Okay, hyperparameter tuning, or at last we could do is that building a good readme. Okay, at last, this is the last we could do it. This is optional. We could do and we could not, like, this is optional. It's totally on our mind. Like, if I get the time, then I will do it. Basically we'll build a good resume, the readme. Okay, that is good. So the first thing that we have to do is to building model, linear regression, linear SMV, then pipelines. Then we could say that evaluation matrices. Okay, getting the evaluation matrices and the right evaluation matrices, and checking that is our data is giving us the best prediction or not. Okay, we have to do that. So we have done with the to-do list. Now let's get understand that what our data actually will do. Okay, so as I told that we had this training set. This is actually used for feeding the model for the prediction. Okay, feeding the model for the prediction and fitting the model. Okay, this training data will go here. Okay, these whole set. Now these we will actually use for evaluation. Okay, for getting the best parameters for the model that will give us the best data prediction. Okay, and let me tell you honest thing, this is off topic, but speaking for that much time I don't know how to speak it, because as the other YouTubers do, and I don't know actually how to speak it in a manner that can engage you, but still I know I'm doing a good thing. Mainly I'm focusing on my communication skill, that how to make you engage, guys, make you sometimes laugh and all this thing. Okay, that is very important, because it cannot be just coding. Okay, yeah, so that is the thing. That first thing, so this is not only used for prediction, but yeah, this is used for testing. This data set, this is used for checking the matrices and then improving the matrices. Okay, this data is used for that. Okay, and then testing the data set. Okay, so let's go, and first of all let's rename a lot of things. So this is our model, we fitted our model. Okay, and for the prediction, okay, model prediction, we will say val. Okay, this is the validation. Okay, validation model one prediction. Okay, and we will use, some of the good matrices that is actually used for evaluation. Okay, so let me first import all the models. See, I have imported all the main evaluation matrices, the R2 score, mean squared error, and mean absolute error. Okay, so let's quickly check all those parameter here. Okay, so actually wait, I would have done it already. Okay, yeah, so you could see that I have actually done it here. Where it went, I've actually done it here, so I will just copy paste it and I won't waste much time writing the code. Okay, yeah, so let me undo it. Okay, yeah, so validation R2 score. Okay, validation MSC, validation MAE, and RMSE also. So we will do nothing but RMSE. So we will np.sqrt do like this, which will give us y test, which means y val, not y test, y val, not y pred. It's this prediction. Okay, so let's copy paste it quickly. This will be y val, this will be y val, sorry, y val, and this is also y val. Let's see, do we get any error or what? Validation RMSC. Okay, so what does it was closed? Wait, have one. Oh yeah, we'll need to give one more. Then again we got a problem. Yeah, we should get a problem. Why should not? Okay, it's nothing, just yeah, as you can see, we can see that we have got our validation set. All the scores for our validation, the R2 score is 0.65, MSC is 4289, this, RMSC is this, and validation MAE is this for the linear regression. Okay, for the linear regression, print linear regression. Okay, this is the thing. Now building the SVM. Okay, support vector machines. It's machine, man, not actually machines, but it is machine. Support machine. Okay, yeah, so what does a support vector machine does? Okay, ooh, yeah, so let's quickly do. Okay, yeah, so support vector machine does is that, yeah, suppose that we have two classes. Okay, and we want to classify the classes. Okay, suppose these are the two classes. So what the support vector machine does is that it creates a line, okay, between the two classes, and it tells and it separates the both classes. Okay, I'm not going into deep that what it does, but actually what it does actually is that taking the distance, okay, taking the distance of these which are the nearest. Okay, suppose where my markers, so these are the nearest points. You can say that these are the nearest point to this class. Okay, and these we could say that are the nearest point to this class. So what is that it takes the distance. Okay, it takes the help of these data points, which we actually call as support vectors, and these, okay, which we actually call as support vector. Okay, and create a line. Okay, this line, create a line like this and separates this and this using its, where it went, yeah, using its margin. Okay, using its margin, which looks like this. Okay, like here I made it, little far, but still, yeah, it does mainly like this. Okay, like this, and again let me copy paste this like this. Okay, so this is what we call as margin. Why it is so bold? Yeah, so this is what we call as margin. But wait, this is actually is for classification. Okay, now if the data is linear, how will it do it? If the data is linear means like this. Okay, wait my graph, let me make it. So suppose linear means this, simply this, that if our data is like this, if our data is like this, wait man, wait, it sometimes it makes me piss off, like it irritates sometimes, and why don't you get at the same setting? Yeah, suppose that our data is like this, it's in the linear form. How will we use the linear regression, sorry, the support vector machine or SVM? How can you classify? Yeah, how can you separate? You cannot use a line for separating classes because we don't have any class here. We actually don't have any class here. What we have is that a linear data. Okay, we don't have a class that we have to classify. We have to classify. Okay, we don't have to actually classify. Okay, so what we actually use is that if the data is linear, okay, and we cannot classify it, then there is like something what we call is that methods. Okay, some are method. I'm not actually telling you the SVM what it does actually is that. Okay, I'm just telling you the overview of it. Okay, so if the data is linear, okay, like this, what we do is that we convert this data into high degree. Okay, we take this data and suppose that we have a function f of x, wait, and why it irritates me sometimes. Yeah, suppose that we have a function x, okay, and it will give us x square, okay, or x cube as we want. It will give us the high degree polynomials that will be like this. Suppose that if we have x square, then what this a quadratic equation looks like? What is the graph of a quadratic equation looks like a parabola. Okay, like this. Okay, my drawing is bit beautiful, but still you I know you could understand it. This is the graph of a quadratic equation or the polynomial which has a degree 2. Okay, and what is the graph of a cubic polynomial? We could say that it's like this. Suppose that we have like this. Okay, we have a graph like this. Okay, we have a graph like this, and what the graph of a cubic equation looks like? Something like this. It always looks like this. Okay, so this is for x square, and this graph is for x cube. Okay, and then it doesn't mean that we only have to do 2x square and x cube. We have to actually, we could use the as big degree as we want, but still according to the data set that we have. Okay, and that we have to do, and for doing that we will import SVR, which means wait a minute, support vector regression. Okay, so from sklearn.svm import, let's see what option do we get. SVR, do we have SVR? Yes, linear SVR. Okay, and what is the difference between SVR and linear SVR? We don't know, but still. Okay, so now let me take you to the book that I was reading, and I actually got to know about these things. Okay, So let's read this documentation, which is very important for building anything, because reading which actually makes sense. Okay, so let me tell you. So I was reading a chapter was fifth, and the book is uh, the hands on machine learning with sklearn, scikit-learn, keras, and uh, TensorFlow. Okay, it was chapter fifth, non-linear SMV. Okay, so non-linear SMV, and it was saying although linear SMV classifier efficient of work surprisingly well in many cases, many data are not even close to begin with linearly separable. Yeah, there are a lot of data set which is not actually linearly separable. Okay, but still we need to make them separate in a linear form, because support vector machine actually does in a linear form, that is separates two classes in a linear form. Okay, and one approach is handling non-linear dataset is to add more features such as polynomial features, as we did in chapter 4. We're not going to go in chapter 4, but still we can say that in chapter 4 we would have done something. Okay, in cases this can result into linearly separable dataset, consider the left plot 5 5. Okay, this it represent a simple data set with one feature. Okay, this is only one feature, x1. This data set not linearly separable, as you can see, but if you had a second feature x2, which x square, the resulting 2D data set perfectly linearly separable. Okay, yeah, we could say that this is a linearly separable. We have one class here and we have one class here. Okay, now moving ahead. Yeah, so this is what I was talking about, how we actually do this. Okay, so this is actually your classifier. Okay, so we will actually use linear SVC also, but still we have, to implement this idea of using the skill, you're going to create a pipeline, creating a polynomial feature transformer, then discuss in polynomial regression page 130 and followed by standard scalar linear. Let's this moon data set overview. So this is the code snippet that we can use for separating the class. Okay, so this is how we can separate the class in SMV. Okay, that is not linearly separable. Okay, then the polynomial kernel, adding polynomial features simple to implement, can work great with all sort of machine learning algorithms, not just SVMs, but at a low polynomial degree. It cannot deal with very complex data sets, and with a high polynomial degree, it can create a huge number of features. Yeah, that makes sense. That if we have more features, then if we use the polynomial degree of high features, okay, then it can make a huge data set. Okay, making the model too slow. Yes, that is true. Fortunately, when we're using SVM, you can apply almost miraculous mathematical technique called kernel trick. Yeah, that is the thing that we use the most. It is explained in the moment. It makes it possible to get same result as you added many polynomial feature, even with a very high degree polynomial, without actually having to add them. So there is a no combinatorial combinatorial. Yes, what is the pronunciation, Matt? Forgive me for the pronunciation. I apologize. Combinatorial explosion of the number of features, since you don't actually add any feature. This is implemented by SVC class, and we don't have to use SVC, but still this code trains an SVM classifier using the third degree. Okay, now we have to use the linear SMV. Okay, Gaussian RVF. So this is what we have to do. Okay, this is what we have to do. This linear SVR. Okay, and RVF where we have SVC. Okay, so so can we say that, can we use linear SVC for our regression problem? Let's see. No, linear cannot be used for, okay. Yeah, for linear classification of classification, as we know that, but yeah, for support vector regression can be linear or non-independent color user. Okay. Difference between linear SVR and SVR. Let's see. I don't think there would be much difference, but still, let's see what is the difference between them. Simply it lies not. Okay. linear SVR and SVR. Okay, these are the things that we have to use, and we'll be using, in a best manner. Okay, as you could see that we have the code snippet for this also, so we'll be using like this. Okay, we have Gaussian RVF kernel. Gaussian is like RVF is like radial basis function, which is actually do something like this. Wait, let me tell you where it went. It actually makes where it went. Yeah, so it actually classifies like this. Okay, it makes actually something like a circle, and then it classifies, not classifies, but it fits it. Okay, then we have a parameter called Appleson. What it is? Okay, so let's equal to 1.5. E is tall. Okay, so tall, not tall, TALL, but tall. See, this is the SVR, the linear, sorry, the support vector regression. So we have our parameters: kernel RVF, degree 3, gamma scale, the coefficient 0.0, the tall means tolerance, C means hypermatter for the tuning. Okay, then Appleson, then we have shrinking, then we have cache size, then we have verbose, max iter, and a lot of things. Okay, so let's go to our GPT, what it tells. Okay, so yeah, the difference between the linear SVR and SVR primarily lies in the type of kernel they use in the application. Linear SVR kernel uses linear by default. This means that it only finds a linear relation between the feature and the target variable. Applications should have a linear tag where the relationship between their feature and the target seems to be linear. Yeah, we have some kind of linear relationship, but still. Okay. Implementation typically faster, more efficient for larger datasets compared to SVR, but no linear kernel. Okay. Kernel can use for linear polymer radial. Okay. Okay. We have different polynomials. Okay. Sorry, we have different kernel can be used in the SVR application implementation. Okay. So SVR, and we have much more kernels. We have linear, polynomial, RBF, sigmoid, pre-computed, or callable. Okay. So these are the what we will say, the kernels. And then we have C regularization parameter that we actually use in the logistic regression also. See, we actually use this kind of regularization parameter for in the linear regression, but it is not same as the logistic regression. Okay, sometimes I don't even know what I'm talking, but still, yeah, it's good. I'll be good with it. Okay, so let's move ahead and let's build it. Okay, so our model 2, which is SVR. Okay, and let's fit it model. Okay, by the way, let's run it and let's model 2 dot fit x train and y train. Okay, we fitted it. Now validation model 2 prediction. Okay, so model 2 dot it will predict fit x val. Okay, not fit, man, I have to predict. I don't even know. Yeah, it's predict, and the next thing it will do is like checking the scores. Okay, we will check the scores. So let's simply copy this what simply copy this and let's paste it. So it's support vector regression validation, R2 score. Yes, so it will be val model 2. We have to just change the model 2 from model 1 to model 2, model 2, model 2, Mean absolute error. Wait, what happened, man? Just right now. Did I made some mistake any? No, nothing. I thought like I copied something else. Okay, yeah. Mean absolute error. This we have to just copy paste here. Copy pasting this and let's see the scores. Scores. Okay. Support vector regression. The R2 score is much worse. It's a negative. And this is actually 6.5. Okay, the MSE is lesser what? It's much more. If you see the RMSE, it is 112730. 112730. So our linear regression is performing best in this case. Okay, is performing best in this case. Now, what we have to do is that we build like this. Okay, now we actually don't have to do like this, but we'll build a pipeline. Okay, we have got this, got that our this SVM is not performing as good as linear regression. Okay, so what we'll go and we'll read. Okay, and let's see what we can do in SVR. Okay, we have the SVM regression. As we mentioned earlier, the SVM algorithm is quite versatile. Not only does it support linear and non-linear classification, but it also supports linear and non-linear regression. The trick is to reverse the objective. Instead of trying to fit the largest possible street between two classes while limiting margin violation. Okay, street is nothing but, let me tell you what a street is. They are telling that this is a street. Street means like this. Okay, this is they're telling as a street. This is a street. Okay, suppose that this is the paints, or you could say the line which divides, this is something that I understand. This is they're calling a street. Okay, this path they're calling a street. Okay, limiting margin violation instances of the street. The width of this street is controlled by hyperparameter E. Not we will say E, but Appleson, I think. Okay, figure 510 shows that two linear SVM regression model trained on the same random linear data on the large margin E equal to 1.5 and other with a small margin E 0.5. Okay, E not E, but Appleson we could say that. And this was the thing, E 1.5 and E 1.0.5. Okay, adding more training instance within the margin does not affect the model prediction. Thus the model is said to be insensitive. Okay, you can use the linear regression scikit-learn's linear SVM to classify perform the linear SVM regression. The following code produce the model represented on the left. This is the training data should be scaled centered first. Okay, the first thing that we have to do that the data should be scaled. Okay, the data should be scaled. Then using the linear SVR. Okay, with Appleson. Okay, so the data should be scaled. So for the scaling, what we'll do is that we'll build a pipeline. Okay, we'll build a pipeline. So from sklearn.pipeline import pipeline. Okay, and let's copy paste because I don't want to waste my time. So this is the pipeline that we'll perform. Okay, so I'll name it SVM regression. Okay, and pipeline. Okay, this is the thing inside a tuple, no, tuple inside a list. Okay, this like this, we'll do like this. Okay, then we have the scalar. So we'll simply copy paste, not copy paste, is just we can write it also. Okay, so scalar, we'll name it a scalar and it will do standard scaling. Okay, we haven't imported it, but still let's import it from sklearn dot pre-processing import standard scalar. Okay, we have imported it. Then what will build that? Our model, okay, which is SVM classifier. So what should we name it? Okay, SVM rig pipeline pipe, could say pipe. Okay, so we will use SVM reg. Okay, and we'll use our linear SVR Appleson equal to 0.5. We'll do like this, and let's copy paste and build another pipeline 1. Okay, pipeline 1, and then another pipeline in which we'll keep our Appleson 1.5. Okay, 1.5, and this our second pipeline. Let's keep it 1 also. Okay, let's keep it 1 and let's see what happens, and we will build another pipeline. Okay, another pipeline in which we'll be using 1.5. Okay, 1.5. So this is the thing. Okay, now we'll do the same thing. Okay, so let's run it. We got error. Yo, wow. Achha, oh, sorry. It's Appleson. It's Apple. Wait, what it is? We have a documentation, man. So epsilon. Oh, it is like this. Okay, we could use 0.1 also. Let's see, man. Let's see what do we. So it's like this. Epsilon. It's not epsilon. Epsilon. Okay. Okay. So this is our 0.5. It should be 1, and so we have actually 4. Okay. So we have 4 pipelines and for the SVM, okay, and 1.5. Okay. So we've got our pipelines. Now let's check its prediction. Okay. Model, no, SVM reg 1. So fit X train Y train. Okay. And let's fit all. Okay. Yo, we have got our first error. That is a very good thing. We haven't defined it. Okay. Okay, man. Okay. Why should not? So all the pipelines, SVR, okay, we have fitted all. Or should I do it one by one? Okay, let's see. Okay, let's see. It's okay. Now we have to predict. Okay, so SVM reg pipe 1 dot predict xval. Okay, so it is SVM pred 1. Okay, we'll naming for storing the variable in the prediction. Okay, and we'll be just copy pasting it. So prediction 2, 2, 3, 4. Okay, pipeline 2, 3, and then 4. Let's run it. Let's see we get any error or not. Now we'll be using for every, now let's just get the score of all this. Support vector regression. Okay, I know that it is of support vector regression, and xval yval Man, validation auto score, SVR, 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 SVR. Okay. So prediction one. Okay, wait, I could use a for loop also. Okay, but still right now I don't want to still right now, but still let's do it by our own hand. Okay, we don't have much time. This SVR1. Okay, so we could say that SVR1, 1, 1. Because we don't have to do it much, but like this, SVR 2, 2, 2, 2, and we just have to change here 2, 2. I will use it. Okay, I will use it the for loop, but still I want to just do it and see by my hand. Okay, is there any difference? Let's see if it does. Then yeah, definitely we will have a good model, man. 3, 3, 3. Okay. We don't have any difference still yet. 4, 4, 4, 4, 4, 4, 4, 4. 5, we are getting all the scores same. Why we are getting all the scores as same, man? We should even get a bit different from each other. Wait, what is happening? We have fitted very correctly. What is the case? Still giving us the same thing. See, what is the thing is that we are not even getting a single different thing. SVM pred 2. SVM pred 2, yes, pred 2, pred 3, pred 4. A lot of things, man. We should get difference. Why we're not getting any, not even like a single, even in decimals. Why? Reg pipe 1, reg pipe 3, reg pipe 4. SVM reg pipe 1, pipe 2, pipe 3, pipe 4, pipe 5. Not 5, but why it is happening like this? Why, man? Why? Let's see, like, do we have any kind of a difference or what? But still, man. See, should we give it all the thing? But yeah, it's showing like this. Y val, X val, we predicted in the X validation, Y validation, SVM. Why we are getting this bad thing? For the linear regression, we have actually a good error. Not like this, but this has a very high, score of error. But why it's happening like this? Like, what? We have trained it very, okay, so let me write, should we scale the linear data before taking the SVR, sorry, linear SVR? Reason for scaling, okay, transformer. Okay, quit it, man. Chat GPT. We'll find it. Write code. What I will say, make a pipeline for linear SVR. Linear SVR, okay. SVR, okay. Yeah, man, same. Wait, we could. Oh yeah, wait. Let me check, dude. No, man, we have actually did it here also. Right, 2, 3, 4. It's good. It's good with different. See, we have actually, if we say that we have built the models, we have pipelines, evaluation matrices we have, but we did not do the hyperparameter tuning. These are the things that we have done, but with different epsilons, okay, which is 0.1, 0.5, then 1, 1.5, different epsilons matrices. Okay. Yeah, grid search CV, okay. Yeah, we'll do it, but man, if I my the thing here is right now like that, if I have done with my own hand, with if I uh coded it, individually, then it should give us the different results. Then why the hell it is not giving us? My issue is like that. Did I did something wrong in or what, man? SVM pred 1, SVM pred 3, this. What? It's right. If I see it's right. Okay, guys. Okay, yeah, so I actually have stretched the video till it's been so long, 45 minutes I think. So I think I should wrap it up. And as I did that, I have completed the building the models, linear regression, linear SVM pipelines. I haven't built it for linear regression, but still I will build it that for also. Okay, as I've done it, and as I'm like, and I'm telling you again that this is not the final and full and fledged project. I'm just exploring in it and seeing that how these values and errors and all the MSCs, all this evaluation matrices are performing here. Once I'm completed with this, I will move to the files, okay, that actually make sense and work for the deployment also. Okay, so that is the thing that I'm telling you. Okay, so yeah man, we'll find in the next videos, we'll find this, that what is the best thing that we could do, okay, for that. And yeah, let's wrap it up, and thanks for watching till right now. Like, if you have any suggestions for me, you could go and write in the comments. That will be very helpful for me. And thanks for watching till right now. And if you haven't joined our Discord, then go and do join the Discord. You will find more enthusiasts of AI there. Okay. And one thing is that I cannot make it public, man, because for making it public, I would need a phone number which I don't have actually. Okay, which I don't have actually a phone number. So that is the thing. Otherwise, I would have made it, public, that you could go and check it and review it. Okay. So yeah, man, that was the thing. And yeah, let's wrap it up. Bye bye. Have a great day.